Now, in the exercises, there is one exercise that I'd like to discuss because it is important. And that exercise asks you to derive the following formula. The number of loops in the Feynman diagram is equal to the number of internal lines minus the number of vertices plus 1. And this, if you remember, when we were counting powers of h bar in the loop expansion, we used this formula. I said that you would prove this formula, and you're going to prove this formula in one of the exercises. So I just wanted to discuss it with you to make sure that all of the ideas are clear. So what is the first thing to realize? Well, L is the number of momenta you integrate over. Number of momenta you integrate over. For each loop in the Feynman diagram, you can have a momentum that flows freely through that loop without affecting momentum conservation. Because the momentum is flowing along the loop, there's no momentum leaking out of the loop. Momentum is conserved, so that momentum is a free parameter. So the number of loops tells you the number of momenta you can integrate over. Potentially, how many integrals do you have? Well, you would have an integral for each independent internal momentum. So let me maybe write it like that. You have an integral for each independent internal momentum. Now, why aren't all of the momenta independent? Well, each vertex has a delta function conserving momentum. So, for example, let's just keep an example in mind, the Feynman diagram that we've already studied. If we have this Feynman diagram and we assign momenta, well, there's P1, that's P2. Here we have P3. There we have P4. And there we have P5. But not all of these momenta are independent because, for example, at this vertex over here, there's an energy momentum condition that we can eliminate P4 completely. We can write P4 in terms of P2, P3, and P1, and we'd have a second vertex there. So how many conditions do we have? There are V conditions on the momenta. Now, each of these conditions could eliminate an internal momentum. And so it's the number of internal momenta that are not eliminated when we've used these conditions that tell us what the number of loops is. So there's V conditions on the momenta. Now, of course, these momenta might affect the momentum of the external lines. So these would be external momenta, or these conditions might affect the internal momenta. And here is my claim. From these V conditions, one sets the overall momentum conservation. And this condition is a condition on the external momenta. Okay? For the Feynman diagram that we have here, this is the one that would set P1 mu equal to P5 mu. So there's one condition that does that. And then there are V minus 1 conditions on the internal momenta. So using these V minus 1 conditions, we can eliminate v minus 1 of the internal momenta. That means we would actually use delta functions to integrate over those. So how many independent momentum integrations do we have left? Well, it's the total number minus the number that we've eliminated, which is v minus 1 of them. That gives I minus v plus 1, and that is equal to L. Okay, so that's where this formula comes from. Now, just to make sure that things are completely clear, okay? Okay, so maybe let's write in one more thing. From this vertex over here, if you look back at our calculation, this is where we got P1 is equal to P5. And from this vertex over here, we got P4 was equal to P1 minus P2 minus P3. So here we eliminated P4 with one of our conditions, and we eliminated P5 with another one of our conditions, okay? This is just again showing you how this formula works. But so you could do this in more examples. I think it's a good thing to play around with. But let's just do another example of a Feynman diagram. Let's pick one with a lot of nice loops. So maybe we'll take this diagram. Then let's do that. And let's do that. So, boy, this looks like it's complicated. So let's take a look. So how many internal lines? So let's count these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 internal lines. How many vertices? 1, 2, 3, 4, 5, 6. 6 vertices. So the prediction for the number of loops is that L would be equal to 11 minus 6 plus 1, and that is 6. So does this diagram have 6 loops? Well, let's take a look. 1, 2, 3, 4, 5, 6. Yep, it does have 6 loops. And of course, this doesn't only hold for diagrams with one external line. You could, for example, have taken this. So how many loops here? Well, the number of internal lines is 2 internal lines. The number of vertices is 2. So the number of loops would be the number of internal lines minus the number of vertices minus 1, and that's 1. And indeed, there's 1 loop. So that works out perfectly. Okay, so I think that was the only really important exercise that I wanted to talk through, just to make sure that you understand how to derive this formula that L is equal to I minus V plus 1. Good. Okay, let's now learn how to actually do the integrations over the momenta.